Varshney. I am professor in Department of Electrical Engineering, Purnima College of Engineering, Jaipur. Today we will see the measurement of resistance which comes in the unit number 4 of electronic measurement and instrumentation of a subjects of 4th semester electrical engineering. So as we know, the resistance is very most important element in electrical and electronics engineering, and its values varies from very small to very high. We can consider the small values resistance as the resistance of the transformer winding and high resistance as the insulation resistance of the transformer winding. Although the multimeter works quite well in the laboratory and it gives the rough value of resistance, but for the accurate values of very low resistance and very high resistance, we need some specific methods. In this lecture, we will discuss various methods of resistance measurement. Let's first categorize the resistance. It can be categorized in 3 categories: the low resistance, medium resistance and high resistance. The low resistance values are lower than the 1 ohm, and the resistance which have the values in between 1 ohms to 100 kilo ohms are considered as the medium resistance, and the values greater than 100 kilo ohms are considered as the high resistance. Let's see our methods are available which are available of the measurement of the medium resistance. These methods are ammeter voltmeter method, Wheatstone bridge method, substitution method, Carey-Foster bridge method and Ohms meter method. In this lecture, I will cover the first 3 methods. Let's see the first method, ammeter voltmeter method. As we know the Ohm's law, the value of resistance R is given by the ratio of V to I. The V is voltage across the resistance R and the I is current flowing through the resistance R. So in this method, we have the 1 ammeter for measuring of current, 1 voltmeter for measuring the voltage. We can have 2 possible connections. Let's see the figure number 1, in which voltmeter measures voltage drop across the ammeter and the voltage drop across the unknown resistance R. So the total voltage that will be measured by the voltmeter is VA plus VR. So the resistance, the value of resistance will be given by V upon I, that is VA plus VR upon I, or I into RA plus I into R upon I, which yields RA plus R. So we get the value of resistance as RA plus R. What is RA? RA is the resistance of the ammeter. Okay, and see now second figure. Let's have a look on the second figure. In this connection, the ammeter measures the current I, which is the sum of the current IV and the current IR. So the resistance is given by V upon I, and that is V upon RV plus V upon R. This is the current flowing through the voltmeter, and this is IR, which is through the resistance R, or we can say R2 is given by R upon 1 plus R upon RV. And if we see the error, which is given by measured value minus actual value upon actual value, which is approximately equal to minus R upon RV. So it can be observed from this expression that resistance is R1 is equal to RA plus R. If we can make RA equal to 0, then we can have the true measurement of the resistance value. And in the second case, if we can make RV is equal to infinite, we can reduce error up to the 0. So in this first connection, we must have R equal to 0, and in the second connection, we must have RV is equal to infinite. Now the question comes in the mind that which connection to be used in the which case. To find out this answer, we equate both the error, and we get RA upon RA is equal to R upon RV, or R is equal to square root of RA into RV. Hence, for resistance greater than that given by this equation, we use first method, and the resistance less than that given by this equation, we use the second method. Let's see the second method, Wheatstone bridge method. This is the simplest and the most basic bridge circuit which we use in the measurement studies. It mainly consists of 4 arms, P, Q, R and S. The P, Q and R, the values of P, Q, R are known, and the value to be determined is denoted by the value of S, which is unknown. An EMF source is connected between the point A and B, while the galvanometer is connected between the point C and D. Just remember the working principle of the bridge circuit, which works on the principle of null deflection. It means we vary a parameter until the detector shows 0 current, and at that condition we use a mathematical relation to determine the value of S, or unknown parameter, in terms of known parameter. At null deflection, no current will be flow from point C to D or D to C, which implies that the potential point of D and C both are equal, and this can be represented by IP into P must be equal to I2 into R. The potential drop at point D is IP into P, and the potential drop at point C is equal to I2 into R, which must be equal at the null deflection. So IP P must be equal to I2 R, and at the null position I1 must be equal to I3 and I2 must be equal to I4, as there will be no current in this branch CD.